So this is lecture 5 on powers and primitive roots in finite fields. So you remember a finite field. A field is a set of elements, numbers, that you can add, subtract, multiply, and divide. Divide means divide by anything except 0. And the real numbers, the complex numbers are examples of fields. They're infinite fields. There are infinitely many real and complex numbers, but they're also finite fields. And then for every prime p, so p is a prime number, the finite field with p elements is the set of classes of integers modulo p. So as representatives, you just take the first p minus 1 non-negative integers, and we have the relation that a and b are the same mod p, or a and b are congruent mod p, if p divides the difference a minus b. So this is the basic example, not the only example, but the basic example of a finite field. And we're interested in powers of elements, mod p. So let's take the example that you find on page 30 in the book. Take p equals 7. So we're working in the finite field with 7 elements. And so F7 is 0, 1, 2, 3, 4, 5, and 6. These are the 7 representatives of the congruence classes modulo 7, where addition and multiplication define mod 7. So 4 plus 5 is 9, which is the same as 2 mod 7. So in F7, we say that 4 plus 5 is equal to 2. And the invertible elements in F7 are the non-zero elements, 1, 2, 3, 4, 5, and 6. So let's start by making a table of the powers of these numbers. First of all, of course, if you take 1 to the first power is 1. I'm writing congruent mod 7. I'm just not writing the mod 7 because it takes up space. And no matter what power of 1 you take, it's always 1. 2 is more interesting. If you take 2 to the first power, it's 2. 2 squared is 4. 2 cubed is 8, which is the same as 1 mod 7. 2 to the fourth is 16, which is 2 mod 7. It's also 2 cubed times 2, and 2 cubed is 1. So this is 2 mod 7. 2 to the fifth. Actually, every time you take a power, you can just multiply the previous number by 2. So 2 to the fifth is 2 times 2 to the fourth, which is 2 times 2 is 4. And 2 to the sixth is 2 times 4, which is 8, which is the same as 1. And I can make this table for all of the non-zero numbers mod 7. 3 to the first power is 3. 3 squared is 9, which mod 7 is 2. Multiply 2 by 3, you get 6. Multiply 6 by 3, you get 18. By mod 7, that's 4. Multiply 3 by 3 to the fifth power. You multiply 4 by 3, you get 12, which is 5 mod 7. 3 to the sixth power, you multiply 5 by 3, you get 15, which is 1. And you can fill in this whole table. And actually, one of the things you'll observe is that the numbers in the middle are different. But if you look at the last column, any one of these non-zero numbers mod 7, when you raise it to the sixth power, you get a 1. And that is an instance, an example of a famous theorem in arithmetic, which is called Fermat's little theorem. So this is theorem 1.24. Fermat is French, so you don't pronounce the T. Fermat's little theorem. And it says that the following, that P be a prime number and A an integer. If you take A to the power P minus 1, that is always congruent to 1 mod P. If A is not 0 mod P, so if P does not divide A, and it's 0 mod P, if P does divide A. Now, the second part is very easy to see, because if P divides A, every power of A also is a multiple of P that is divisible by P, and so it will be 0 mod P. So the hard part is to prove that if P does not divide A, then A to the P minus 1 is always divisible by P. So that's really the main part of this section of the text, the proof of this theorem. And the proof is very nice. So the idea is the following. Consider the numbers. So we have a number A that's not divisible by P. So consider the numbers 1 times A, 2 times A, 3 times A, 4 times A, up to P minus 1 times A. So take A and look at all the multiples by the non-zero congruence classes mod P. 1 times A, 2 times A, 3 times. I claim that these are distinct mod P. And the proof of that statement is the following. If J and K are numbers between 1 and P minus 1, and J times A is equal to K times A mod P, that means JA is congruent to KA mod P, what does this mean? Then P divides the difference of these two numbers. That's what congruence means. So P divides JA minus KA, which, if you factor out the A, is J minus K times A. So P divides this product of two numbers. By Euclid's lemma, if a prime divides a product of two numbers, it must divide at least one of them. So either P divides J minus K or P divides A. But we chose A not divisible by P. So P doesn't divide A, which means P divides J minus K, or J is congruent to K mod P. But what do we know about J and K? So on the number line between 1 and P minus 1, you have J and K. The furthest apart they can be, the absolute value of J minus K, is at most the distance from 1 to P minus 1. It's at most P minus 1. And a number, and it's at most P minus 1. The only way this number is divisible by P is if J minus K is divisible by P or J equals K. Because if J and K were different, this would be a positive number between 1 and P minus 1, and no such number is divisible by P. no number between 1 and 6 is divisible by 7. So this proves that these numbers are distinct. Also, they're not divisible by p. So if a and p are relatively prime integers and p is a prime, then a, 2a, 3a up to p minus 1 times a are distinct mod p. And they're non-zero. But the numbers 1, 2, 3 up to p minus 1 are also non-zero and distinct mod p. So here I have p minus 1 numbers, and here I have p minus 1 numbers. And they're distinct mod p, but they're only p minus 1 numbers distinct mod p. So the sequence of numbers a, 2a, 3a up to p minus 1 times a is just some rearrangement or permutation of the numbers 1 to p minus 1. Which means if I multiply them all together, a times 2a times 3a up to p minus 1 times a, that's the same as the numbers 1 times 2 times 3 up to p minus 1 mod p. Because these numbers are just these numbers in some other order, but multiplication is commutative, so it doesn't matter what order you put them in. This product is equal to this. Now on the left-hand side, I have a occurring in each factor, and they're p minus 1 factors. So if I factor out the a, I have a to the p minus 1 times 1 times 2 times 3 up to p minus 1, congruent to 1 times 2 times 3 up to p minus 1 mod p. Or I can use factorial notation. It doesn't really matter, but a minus 1 times p minus 1 factorial is congruent to p minus 1 factorial mod p. And p minus 1 factorial is not divisible by p. If p were to divide this product, it would divide one of the factors, and these factors are all strictly less than p and at least 1. So this is not 0 mod p, so I can cancel it. And when I cancel, I get a to the p minus 1 is congruent to 1 mod p. So that is a proof of Fermat's little theorem. And it is extremely important in cryptography, in codes. Let's just look at a couple of examples of this. If I take, for example, p equal 5, 3 is not divisible by 5. So p equal 5, a to the 5 minus 1, a to the 4th is congruent to 1, mod 5, for all a, such that 5 doesn't divide a. So for example, 2 to the 4th is 16, is congruent to 1 mod 5, because 16 minus 1 is 15. It's 5 times 3. 3 to the 4th, 3, 9, 27, 81, congruent to 1 mod 5, because 81 minus 1 is 80, which is 5 times 16. 4 to the 4th, what's 4 to the 4th? That's 2 to the 8th. 2 to the 8th, I think, is 256. It's congruent to 1 mod 5. because 256 minus 1 is 255 is 5 times 51. Suppose I take p equal 11. So 2 to the 11th should be 2 to the 10th. If p is 11, p minus 1 is 10. What is 2 to the 10th? That's 1024. This should be congruent to 1 mod 11. Is it? Well, 1024 minus 1 is 1023. If I divide 11 into 1023, what do I get? I get 9, 99, 33, 33, perfect. This is 11 times 93. So this is true. 1024 minus 1 is divisible by 11. Now the numbers get bigger. It's harder to figure out. Let's see. 3 to the 10th, that's 3 to the 5th squared. Let's see, what is 3 to the 5th? 3 to the 5th, 3, 9, 27, 81 is 243. Actually, 243 is congruent to 1 mod 11, because 243 minus 1 is 242. If I divide that by 11, I get 22. So 3/5 squared, which is 3 to the 10th, is 1 squared is 1 mod 11. This is an interesting example because by Fermat's little theorem, we know without having doing the calculation that 3 to the 10 is congruent to 1 mod 11. But in fact, a smaller power of 3 is congruent to 1. 3 to the 5th is congruent to 1 mod 11. So this is not a contradiction. This is just a fact, an observation. 3 to the 5th is congruent to 1 mod 11, and 3 to the 10th is congruent to 1 mod 11. So 10, 3 to the power 10 is 1 mod 11, but 10 is not the smallest power of 3 with that property. And we give a name to the smallest such power with that property. And it's as follows. So P is prime, and A is an integer, and P doesn't divide A. So what is called the order of A mod P is the smallest positive integer. N, such that A to the N is congruent to 1 mod P. So we know that N equal P minus 1 works, but there might be an even smaller number, as you saw in the case with 3 and prime 11. So the order of A mod P is the smallest positive integer N such that N divides A to the N is congruent to 1 mod P. And there's a nice proposition, proposition 1.29, which says the following. Actually, let me just change the notation. So the order of A mod P, I'm going to put the smallest positive integer K, such that A to the K is congruent to 1 mod N. And if K is the order of A mod P, if A to the N is also congruent to 1 mod P, then K divides N. So if K is the smallest positive power of A, that's congruent to 1 mod P. and n is any power of a that's congruent to 1 mod p. K has to divide n. And the proof is as follows. So we're given that a to the n is congruent to 1 mod p, and a to the k is congruent to 1 mod p. Suppose we divide n by k. So by the division algorithm, n is k times some quotient plus the remainder, where the remainder r is between 0 and k minus 1. So a to the n, which is a to the k cubed plus r, this n is k cubed plus r. This is a to the k cubed times a to the r, just by rules for exponents, which in a to the k cubed is a to the k to the power q times a to the r. But a to the k is 1. So this is 1 to the q, a to the r, and 1 to any power is 1. So this is a to the r. But a to the n is congruent to 1 mod p. So a to the r is congruent to 1 mod p, and r is between 0 and k minus 1. But k, the order, that's the smallest positive power of a, which is 1 mod p. If r were positive, it would be smaller than k minus 1. So r cannot be positive. That means it has to equal 0. So r equals 0, and n equals k times q. So if k is the order of a mod p, and a to the n is congruent to 1 mod p, k divides n. So a special case, we know by Fairmont's theorem that a to the p minus 1 is congruent to 1 mod p. So just take p minus 1 to be equal to n. So k divides p minus 1. So every element which is not 0 mod p can be raised to a power to give you 1 mod p. By Fairmont's little theorem, a to the p minus 1 is always 1 mod p. There may be a smaller integer k, a smaller exponent, such that a to the k is congruent to 1 mod p. But it's always the case that such a k will be a divisor at least of p minus 1. So there's several more very useful related observations. Let's go back to the case p equals 7. If I look at the powers of 2, 2 to the 1 is congruent to 2. This is all mod 7. 2 squared is congruent to 4. 2 cubed is 8, which is congruent to 1, mod 7. So when you look at the powers of 2, you get 2, 4, 1, and then it repeats cyclically. If I take 3, 3 to the first power is congruent to 3 mod 7. 3 squared is 9, which is 2 mod 7. 3 cubed is 2 times 3 is 6 mod 7. 3 to the fourth power, 3 to the sixth, because 3 times 6 is 18. 18 is 4 mod 7. 3 to the fifth is 12, which is 5 mod 7. And 3 to the sixth is 1 mod 7. So if I look at the powers of 3, 3 to the sixth is 1, 3 to the squared is 2, 3 to the first is 3, 3 to the fourth is 4, 3 to the fifth is 5, 3 cubed is 6. So every non-zero number, non-zero mod 7 integer is a power of 3. So if you wanted to find all the non-zero congruence classes modulo 7, it's enough just to look at the powers of p. If you look at the powers of 2, it doesn't work. The powers of 2 only give you 1, 2, and 4. But the powers of 3 give you 1, 2, 3, 4, 5, 6. Let's look at another example. Suppose I take p equal to 11, and I'm looking at the finite field F11, or Z mod 11Z. What are the powers of 2? 2 to the first power is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16, which is 5 mod 11. 2 to the fifth is 10. Let's keep multiplying by 2. 2 to the sixth is 20, which is 9. 2 to the seventh is 18, which is 7. 2 to the eighth is 14, which is 3. 2 to the ninth is 6. And 2 to the 10 is 12, which is 1. So if I look at the powers of 2 mod 11, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Get them all. What happens if I look at the powers of 3? 3 to the first power is 3. 3 squared is 9. 3 cubed is 27, which mod 11 is 5. 3 to the fourth is 15, which mod 11 is 4. 3 to the fifth is 12, which mod 11 is 1. So I take the powers of 3, I get 3, 9, 5, 4, 1, and then it's going to repeat. So I can only get 5 different numbers mod 11, non-zero congruence classes mod 11. But with powers of 2, I get them all. And we say that an integer g is what is called a primitive root. Modulo of prime p if you look at all the non-zero congruence classes mod p, they're all powers of p. 1, g, g squared, g cubed, up to g to the p minus 2. G to the p minus 1 is 1. So we say an integer g is a primitive root mod p if every non-zero congruence class mod p is a power of g. So in these examples, we see 2 is a primitive root mod 11. 3 is not a primitive root mod 11. And a very big theorem in number theory, which I'm going to use but not prove, is that every prime has a primitive root. Primitive roots exist. They might be hard to find for a large prime number p, but the theorem says that for every prime p, there's at least one number g that's a primitive root mod p. And that's nice to know. So this is all very important, but it's not too long. But there's a lot to think about in these couple of pages, and again, the more you think about it, the more you understand the problem. That is it for this lecture.